My name is James Arthur. I am the CEO and one of the co-founders of Vaxine. So Vaxine is a new VC-funded, open-source Erlang and Elixir company. We are developing a rich-CRDT database system. So I will just give you a sense of I'll just give you a sense of the team, sorry. Just briefly, I won't talk through everybody, but you might see some familiar names or faces there. And you can see that, in a sense, we're covering from research, industry experience, and company building. And for what it's worth, these are our investors, who are awesome early-stage deep tech software firm based in Berlin. And before I really jump in, I just want to orientate you on what the project is, what we're talking about. So Vaxine is a geo-distributed active-active database system. It's based on AntidoteDB, which is developed in Erlang. We're building layers on top of it in Elixir, and we're integrating Antidote with Ecto for a relational developer experience, and we're providing additional invariant safety using rich-CRDTs. And with CRDTs, people often think of offline first, kind of local software in the client. That's not what we are. We are an online cloud database system. The CRDTs are in the database on the server. Okay. So for the talk today, I basically want to convince you that when the Vaxine project matures a little bit, because we still are relatively early and we're working out to build out what I'm describing today, but when we do that, I want to convince you that Vaxine is going to be the best database for geo-distributed LiveView applications. So I hope that's interesting if you're building LiveView applications. If you're not building LiveView, I hope the LiveView case is still interesting to showcase some of the interesting aspects of the database system. So let's jump in, just talk a little bit about LiveView. LiveView is, in a way, an interesting approach to app development, because at first glance, it's suboptimal, right? You have the network on the interaction path, so you need to go over the network to basically run your code. But then on the other hand, it obviously slashes complexity. You work in a single language, you cut out that whole Webpack, React kind of stack, and for me, for example, just as a generalist software developer, it's much more productive than doing that sort of full stack front end and back end stuff. I'm 10 times faster building out a dashboard in LiveView than I am in React. But if we could just come back to that key limitation, right, that the network is on the interaction path. What that means, as you know, is that the responsiveness of a LiveView app, whether it feels snappy or whether it feels snuggish, is highly dependent on network latency. Now, if you have an app server in Stockholm and your users are here in Stockholm, it's not a problem, right? You don't have a problem with that, but we tend to build internet systems, and once the latency goes up into that kind of 100 to 300 millisecond range, that's when the application starts to feel sluggish, right? And these are actually just ping times from Stockholm to other cloud regions, so that doesn't take into account the last mile. It doesn't take into account things like TCP congestion, let alone the time it actually takes your application code to run. So basically, latency is a challenge with getting LiveView apps to feel responsive. So the obvious thought is to geo-distribute your application server, right? So you move your application server close to your users, and you cut out that network latency. And for what it's worth, we're not in any way affiliated with either Fly or Phoenix, but it's probably one of the reasons why there's a good synergy between the two, because you have LiveView driving the need for a geo-distributed application hosting platform. Now, the challenge is you've moved your app server close to your users, but if your business logic still needs to talk to your database, you still have the latency from the app server to the database, right? And actually, if your request handler or event handler maybe makes multiple database requests, you've actually made the latency worse by moving the app server close to the user. Now, there's two main solutions at this point. You basically have a world of optimistic writes and tentativity, or you can move your database close to your app server. And so for this talk, I'm not going to talk about optimistic writes, just mainly for time, but partly because it's mainly a front-end development pattern, and also introduces a bunch of complexity handling the failure path code from the tentativity, and we're trying to basically make application development simpler. So let's focus on the second option, which is moving the database close to the application server. Now, this works pretty well for two scenarios, right? The first one is reads. So you can use read replica fan-out. And the second one is geofencing. So if you can bound your data model to keep the data for a specific user or customer or tenant within the region, then you can have low latency reads and writes with geofencing. But the challenge is that actually neither of those two cases are really the common case when you're building out an application. Because if you're building an interactive application, you still have latency on the write path. So obviously applications have different balance between read and write workload, but if you have a significant write component in your interactive application, read replicas don't solve write path latency, obviously. And then with geofencing, it limits the ability to share data between users who would be in different regions, obviously. And also, it often introduces these boundaries in your data model, which mean it's difficult to query across them, run analytics, for example. And also, what looks often at first like a kind of neat geofence data model, as your requirements evolve over time, it can often introduce a whole load of operational complexity and technical debt as you find yourself having to engineer around those boundaries. Whereas what you really want is you want an active-active system where you can talk with low latency on both the read and write path, and you don't have those artificial boundaries in your data model. But here we are. We started off trying to make app development simpler, and we just wanted a reasonable amount of kind of snappiness for our app. And suddenly, we're looking at a geo-distributed active-active database, and that takes us into the world of the CAP theorem and a whole world of complexity. So as you know, with the CAP theorem, because partitions are inevitable, you essentially have to choose from a trade-off between consistency and data integrity, or availability, which correlates to low latency. And so for these type of active-active database systems, you have CP systems like Spanner, Cockroach, Fauna, etc. And they're active-active, so you can have a database server next to your app server, but they coordinate to maintain consistency. So actually what will happen is in practice, they'll make 2 network requests to a quorum of the other regions. So you started off with a Postgres system, you've moved to a much more complex geo-distributed database system, and actually it's made your write path latency an awful lot worse, because you've got maybe 4 times the amount of network requests going on. So you come at it from the other side, which is AP systems, like, for example, Yugabyte in cross-cluster mode, or a specialist CRDT database like Macrometa. And they can accept both reads and writes with low latency, and then replicate data between regions asynchronously in the background. And this looks like we finally have a solution, right? Because actually we can now move our database close to our application servers, and we have low latency on read and write path. But at what cost? And the cost, as we know from the CAP theorem, is consistency and data integrity. Like AP databases, they talk a lot about, say, clock synchronization, timeline consistency, last write wins, and it sounds sensible, right? Last write wins, last write kind of should win, right? Because it's the most recent write. But like last write wins, for instance, as a consistency semantic, just applies to individual fields. And the real challenge that comes with these AP systems and data integrity comes from concurrent overlapping updates that affect multiple fields. So I'll give you a couple of examples. This first one is just a simple one showing basically why an AP database can't have a unique constraint. So the point is that, so we simplify it to 2 regions. We have a region in America and one in Japan. And if a user comes along and wants to set their username to Dave in America, then that transaction is valid from the perspective of the American region. But if at the same time a user in Japan also wants to set their username to Dave, that transaction is also valid, and you only get the data integrity violation when they're asynchronously replicated and you try and merge them in. And at that point, if you wanted to have, say, globally unique usernames, you just can't have it. An AP system can't provide that. I'll give you another example, classic example from the literature. So this is a data model where you have a set of tournaments, and then you have players who can enroll in the tournaments. And so you can imagine in America, you have one concurrent transaction which removes the tournament, whilst in Japan, a player enrolls in the same tournament. And both of those transactions are individually valid at the clusters that they're applied, but when they're they're replicated asynchronously and merged in, you end up with a referential integrity violation because the player has enrolled in a tournament that doesn't exist. And in a sense, the key point is that you can't just reject the invalid writes, because by the time you've discovered them, it's already too late. If you have accepted the right in one region and then you reject it in another, you have inconsistent data between the regions. Whereas if you accept both of the rights in all places, you have a data integrity violation. And it's all the stuff that basically gives weak and eventual consistency a bad name. And it's why Postgres is the default, right? Because elephants never forget. You don't end up in these kind of weird data states. And you can trust it not to lose your data. So again, we started off looking for simple app development and just a reasonable amount of snappiness. And now we've got the complexity of an active-active database system, but it can't actually maintain simple stuff like unique constraints, check constraints, or referential integrity. So it sounds like we need to go back to the drawing board, right? What do we actually want? What is the requirement? What's the spec? We want a relational database that we can use from Ecto. We want it to be geo-distributed, so the database is close to our application servers. We want low latency on both read and write paths. So it needs to start from an AP perspective. We want the same consistency model that we can trust. And we want the database to be able to actually guarantee standard invariants like constraints and referential integrity. And as you've probably guessed, that's what we're doing with Vaxine, right? That's what Vaxine is. That's what we're building. So Vaxine is a geo-distributed active-active database. It's based on AntidoteDB. AntidoteDB is a planet-scale geo-distributed database. It's designed and built by some of the world's leading database consistency academics, including the co-inventors of CRDTs. And it's been stewarded over the last decade or so by Professor Annette Bieniusa at the Technical University in Kaiserslautern. It implements the CURE protocol of TCC+. TCC+ means transactional causal plus consistency, so transactional causal consistency with CRDTs. And it's formally proven to be the strongest possible consistency model for an AP database. So basically, this is what gives us geo-distribution, low latency, and a sane consistency model. And then as TCC Plus is a cure for consistency under partition, Antidote implements the cure protocol. Vaxine is a delivery method for the Antidote. And what do we mean by that? So what we mean is taking Antidote, productionizing it, adapting it to a standard relational developer experience, and adding back on those standard database guarantees. So it works, so it's easy to use, it's easy to code against, right? It's just magic. So what do we mean by the developer experience? Well, you can basically use it from Ecto like this. So this is a simple account schema that will be familiar if you're just used to working with Ecto. It has two fields, a name and balance, and the account belongs to a user. So just to highlight a couple of things in this simple bit of code, you have, say, the name field is a string, which is a built-in Ecto type, just a primitive type, whereas the balance field is a custom CRDT type, in this case a counter. You can define the relationships using standard Ecto associations. And if you look at the change set function towards the bottom, you can see that you can work with either the primitive types or the CRDTs through the standard Ecto change set interface. And either you can cast assignments to the CRDT types, or we provide custom cast functions when you want to be more precise about the operations that you're providing to the type. And then, so how do we do the database guarantees, referential integrity, check constraints, unique constraints, etc.? Well, it's using rich-CRDTs. So rich-CRDTs are basically, by definition, CRDTs that are extended to provide additional database guarantees. They were invented and been pioneered by my co-founder, Walter Belegas, working under the supervision of Mark Shapiro and Nuno Preguier, the co-inventors of CRDTs. And there's basically three primary rich-CRDT techniques. The first is kind of familiar. It's composition, where you take basic CRDTs and compose them into higher order CRDTs in order to provide certain merge semantics or invariant safety. A very simple example on the side there is a positive-negative counter, which is composed out of two individual counters. More realistic examples would be like a text editing CRDT, or for example, a CRDT map, which you can then, you have the map as a container, and then you can compose so the keys map to specific sub-CRDT types. And then compensation, so the second technique. Compensations are where the database system proactively injects operations into a user transaction in order to leverage the concurrent merge semantics to provide the invariant safety. So if we go back to the example that we showed before about referential integrity violation with the tournament and player enrolling model, with compensations, you can basically fix it if the system injects a harmless touch tournament operation into the transaction that enrolls the player. So what happens then in America, you have a remove tournament operation. In Japan, you have a touch tournament and an enroll inside a transaction. And when those are concurrently merged, if you specify add wins semantics on the tournament set, then the tournament is preserved and you don't have the referential integrity violation. So it's just one example of how you can use compensations to, for instance, preserve an invariant such as referential integrity. And the techniques vary depending on the consistency semantics that you want to maintain. And then the third mechanism, which is maybe the most important, is reservations. So reservations, if you know it, is like a generalization of the bounded counter mechanism. It's when you share out rights to perform operations across your distributed clusters. And so a great example is ticket sales. Say you have 10 geo-distributed clusters and you have 1,000 tickets to a concert. You can share out 100 rights to each cluster, and they can merrily sell tickets without coordinating with any of the other clusters until they run out of rights. But the key thing is that what you can also do in the background when you're operating the database system is monitor the use of the reservations and proactively rebalance them in order to avoid having to coordinate in order to get reservations to perform the right operations. So you basically, reservations they do introduce runtime coordination as a fallback in order to provide consistency, but operationally and in terms of the design of them, you try and avoid coordination as much as possible on the hot path of your application. And I've left just one up here to just demonstrate. There's three types of reservations. There's a kind of escrow mechanism. You can also have an escrow mechanism with additional algorithms, and you can also have mutual exclusion or locking. So locks are basically a special case of a reservation system with just one right. And so you can see if you were performing an operation in Japan and you didn't have the single right, you'd have to acquire it. But basically, that's the kind of worst case latency for our system, which is equivalent to the best case, which is equivalent to the kind of latency you would have with a CP system, for example. And now if we come back to the schema that we showed earlier, you can see that basically each account row is stored as a CRDT map, which is an example of composition. The unique constraint on the name field is guaranteed using reservations. And referential integrity between the account and the user it belongs to can be guaranteed either using compensations or reservations, depending on the consistency semantics which you're after. And so now I'll just touch very briefly on our stack. So you can see at the top here, you have Elixir applications like Phoenix or Absinthe. They use an Ecto interface as standard using our Vax Ecto adapter. That talks to our Vaxine layer using standard repo.update, repo.insert functions. The Vaxine layer is then where we map between the relational model and the underlying CRDT storage, and it's also where we can introduce these rich-CRDT techniques so that we provide the invariant support there without leaking the complexity higher up the stack. And then at the bottom, the antidote layer provides persistence, sharding, replication, etc. And also, if you look at the bottom right here, you can see that we are building in a real-time subscription mechanism on top of the existing AntidoteDB replication system. And if you look at it in a LiveView context, this is another example of a very simple LiveView where we're using the account schema that we defined previously. So we're taking the current user ID, looking up an account, assigning it to the socket, and the render function then takes care of just rendering the balance. If you change that, the last line at the bottom there, to this, we leverage the LiveView attach handler functionality to mean that now when anybody anywhere in the world makes a write to that same account row, your LiveView will automatically re-render. So you get built-in real-time collaboration based on a low-latency geo-distributed database, all based on conflict-free data types. And it's a model that, because when you write to our system, you write with absolute certainty, and you do so potentially from the same server that your LiveView backend app is, it can eliminate a whole class of flaws and anomalies and rollbacks that you get using other approaches to build snappy multi-user applications. So with, for instance, a strong consistency database, you'll often do a write, render it to the user, and then the transaction is rejected, and that's an abort. And we can totally avoid that by only displaying the updates to the user once they've already been confirmed by the database system. So that was my argument. I hope the combination of low latency, consistency, and integrity and built-in real-time collaboration has convinced you maybe to take a look at Vaxine, maybe in 3 to 6 months' time if you're building a LiveView application. And I hope also just sort of longer term, you can see what we're trying to do is take the strongest possible AP CRDT database tech and basically strengthen it and productionize it so it can be used for more mainstream application development. And also that you can see from the type of rich CRDT techniques how we're trying to engineer around the constraints of the CAP theorem. As I said, we're very early. We're developing in public on GitHub. Everything's Apache 2 open source. You can see this is our website. That QR code, if you want to scan it, takes you directly to our website. We're vaccine.io. We're on GitHub under the Vaccine.io organization. Twitter, we have an open public Discord, so you're very, very welcome. If you're interested in the project, please come along, join the Discord, say hi, ask any questions. The whole team is just hanging out there. And also, I just want to highlight that 3 of my colleagues are also here at the conference. So my co-founder, Volta, and Vasily and Felipe, who are probably all here in the audience. So please, if you're interested, again, very welcome. Please come and find us, talk to us. We'd love any feedback on the project, any ideas you have for it. And also, if you have ideas about where you might use this or good use cases for it, we'd love to hear any suggestions. Thank you.
People in this room can hear me anyway. And I will speak here so that the people on the internet also hear me. I have no questions in the... No, I have a question in the... Yeah. Here we go. How do you do migrations? Man, I've been talking about the ice cream all along, and I forgot I had another mic. Yes, so how do you do migrations?
It's a good question, and a migration system is one of the things that we need to build in so that we know what the data schema is in order to be able to provide the invariant safety and know which constraints we want to maintain. We have a number of ideas. We haven't built it yet. We've got a number of ideas around the design of the system. For example, there's the Cambria project, which is a very interesting approach to being able to evolve migrations in a distributed database system. And so that's one of the inspirations, but we basically haven't got to the bottom of that yet. Yeah.